Welcome everyone. I first thank the organizer for giving me this opportunity to talk about our work here. So today I'm going to talk about correlation and fluctuations in single fine motion under resetting. So this work is done in collaboration with Prashant. Most of you know him. So Prashant was a PhD student here, now he's in Niels Bohr Institute. Okay. So let me start with the definition of single file motion. So the motion of particles in narrow channels, but the particles cannot overtake each other, is referred to as single file motion. So that is actually shown in this schematic figure also. So the narrow channels is shown by these two blue horizontal lines, and the solid circles denote the position of the particles. So here the particles actually can't cross each other. So, and this motion actually called single file motion. Now, where do you see this kind of motion? So here you can see like non-overtaking vehicles in this lane. Like here, you do, like the vehicles don't have the space to overtake any other vehicles. So as a result, the order of the particles remains intact. So you can see this in Q also. Like so here, even if you have the space to overtake, but you should do this overtaking here. Okay. Now, due to this non-overtaking constant, the physics actually changes quite drastically. Like here, you don't only get quantitative changes, but also get some qualitative changes as well. Now, let's understand it with an example. So these are the trajectories of 5 independent Brownian particles, so denoted by 5 different colors. So the position of the particles are plotted as a function of time. So here you can see the crossing is allowed. Okay, so if you see this green trajectory, so here you can see like the crossing is happening, and it can cross the other colors also and all the other particles also. So here, if you compute the mean square displacement of this, let's say green particle, so here you get the diffusive scaling that we all know, like it goes as 2 dt. Now, if you consider the following situation, where the overtaking is not allowed. So here you can see that the green line is always in between this blue and the brown particles. So here, if we compute the mean square displacement of the same particle, like this particle, then it actually changes to subdiffusive, like the mean square displacement goes as xi square root t. Now, often this single file motion system described by this random average process model. So the model is actually shown schematically in this figure. So the circles actually denote the position of the particle in a one-dimensional array, and these are the position of the particle at any instant time t. Now, if we want to know the position of the particles at later instant, let's say t plus dt, then the evolution rule is written in equation 1. Now, what does this rule actually tells? Like in the interval like t to t plus dt, the particle ith particle actually jumps to its right with this probability p dt by some fraction of the space available to it. Like it can't cross, so it can jump some fraction of the space available to its right, and with the q dt probability, it can jump to its left again some fraction of the space available to it. So that is actually written here, and eta I are the random numbers taken in between 0 and 1, so such that the particles can't cross, so the ordering remains intact, and with the rest of the probability like 1 minus p plus q into dt, the position of the particle stays there. Okay, so in this case, in this reference, the authors computed the mean square displacement as well as correlation also. Like if you see this mean square displacement, that actually grows with square root t, like it grows with time. And if you see the coefficient, like here it is the p plus q, that is the jump rate to left and right. So that actually comes in this form, like p plus q. And again, in the correlation also, like this is the z0, like z I square term, and there is some scaling function. So here also you can see like p plus q comes, like p and q comes in this form only, like p plus q times t. Here also like you can see like p plus q times t. So here you can scale it accordingly, like you can put like p plus q equal to 1 and compute the and do the computation. So here you won't see any difference if you put p plus q some constant and change p and q separately. Okay, so that behavior is there. So you won't be able to distinguish between the symmetric case and the asymmetric case, as long as you keep fix this sum p plus q. Okay, now we want to see this effect of this, now we want to see the effect of resetting in random average process model. Like how does this, how do the quantities change as a function of time? Okay, so mu1, mu2 are the like moments of this distribution of theta. Sorry, okay. Okay, so we wanted to see the effect of resetting in this model. Okay, so before going to the results and all, like this is just a slide for resetting event. Like resetting actually helps in searching process. Let's say you are in this position x0, and this is actually the position of the target, and you want to find the target in, that is your goal. Now, if you do just random work, simple random work, then the average time you take to reach this target, that is actually infinite. That we know, like starting from x0, there is finite probability that without crossing this line, you go to this plus infinity. So for that, the average mean time to reach this line actually becomes infinite. However, if you do the Brownian motion, but in presence of resetting, then the average time, like the mean first time, actually becomes finite, because like due to this resetting, you stay near close to x0, and you won't go to this plus infinity, and in some time you will reach this target in some finite time. Okay, so due to this resetting, the evolution rule actually changes. Like with this probability, you reset to your initial position, and the rest of the probability you do the random average process. Okay, now as just recall, like we are interested in computation of mean square displacement and correlation in this system. Okay, so this is the values of the mean square displacement. This is for the symmetric case, like p equal to q, and this is for the asymmetric case. Now here you can see, like starting from 0, they will saturate to some finite value. So that is expected, because they are doing random average process, and as well as they are undergoing resetting events in between. Now, but if you see closely, like these two cases are quite different in terms of that how do they saturate to their equilibrium values. So for that, what we did actually, we subtracted out the instantaneous value of the mean square displacement from its saturation value, and look at this quantity dt. Now, if you see, like for the symmetric case, it actually decays in this way, like exponential of minus RT by square root t, whereas for the asymmetric case, it is like t to the power minus RT. And you can see, like it appears in this way, like p minus q square. So earlier in the original random average process model, we had like p and q are coming like p plus q form. So here it is not the case, and you can completely distinguish the symmetric case and the asymmetric case, and the functional forms are also quite different. Okay, and this distinction of this symmetric case and asymmetric case also appear in the correlation between two particles. So this is actually shown in this way, like two particle correlation. It actually decays exponentially, and for the asymmetric case, there is some contribution. Like if you put p equal to q, then for the symmetric case, it terms is 0, and you get just exponential decay, and this term actually, and the correlation actually decays to 0 when you put I sufficiently larger than xi p. However, for the asymmetric case, you get that like even you put I equal to infinite, then actually this correlation decays to some finite value. So that is actually quite distinctive from the original random average process model also. Like these two cases are completely different, and we computed this correlation function and all quite explicitly in this case. Okay, so the conclusion is that we look at the effect of resetting in an interacting many particle system, that is actually called random average process model. We look at the mean square displacement as well as the correlation between two particles, and what we found that the approach of their saturation value, that's actually quite different in the symmetric case and the asymmetric case, and that is also appear in the correlation function as well. Okay, thank you.
Questions? Okay, actually I'm just going to continue my question about this mu1 and mu2. How exactly are they defined? Is it mu1 the average of eta and mu2 is the standard deviation?
Just no, not standard deviation, it's like eta square p of eta d eta, like the second moment, not cumulant.
The variance?
means mean square position, not the displacement. Like this.
Yeah, we can.
Eta square eta deta. It is not. It is just a moment, not cumulant.
Okay.
Second moment.
Okay. And this statement about asymmetry, you know, like I didn't quite get it. The statement is that when you have asymmetry, when P is not equal to Q, you have some
different behavior.
For example, you're showing that there's some long range part in the 2-point function.
Yes.
Could you give me some physical picture of why that is true? Like why there is some long range correlation when you have asymmetry?
Okay, so in this case, like when the particles are resetting, like all the particle reset at a particular time only, like the particle reset to their initial position. But for P not equal to Q, there is some drift also. So as a result, what is happening? Like the particles are actually the overall system actually going in this way and suddenly comes back to these resetting events, resetting points. Okay, so as a result, like even though the particles are even far from from the other particles, but due to this overall drift, there is this long range correlation. However, for the symmetric case, the system is actually like doing this kind of things, like not changing very much. But for the asymmetric case, there is some overall drift also. So as a result, two particles become correlated.
Take away the drift by just, you know, like going to a moving frame. Isn't it just a constant drift?
No, here. Yeah, that might be true. Yeah, this is this overall drift, so we can subtract out. But one thing I just want to mention, like here already this part, like the mean position is already subtracted out, like the mean position of Z0 and Zi, that is already subtracted out. But still there is some contribution.
Actually, I have some confusion about what sort of boundary conditions are you putting on the full chain? You must, is
like
it some infinite chain?
Infinite chain, yes. You won't see this effect for small n also, like this figure also, you won't see this distinction for small n. Because like if you give sufficient time, like they will be very far from each other. So
yeah, in that case, in this problem, that the fact that all the particles are ordered in the sense that they can't cross each other, wouldn't the correct degrees of freedom would be to use the difference between the successive positions as a good variable instead of individual? I mean, maybe eventually that's how you do the numerics.
Like even like also we are doing this kind of thing, like we are interested in this quantity, like from the very I mean the average position is subtracted out. So
that's true, but I would have thought that it's more meaningful to talk about differences between the two particles as the correct degrees.
Yeah, so that is actually happening, like, and even if you see the rules, like this is the so that is actually happening.
Okay. Just one question. What is the role of initial conditions in, I mean, you reset to a specific initial condition, right? Yeah. How important is the choice of initial condition for the rest of the results?
Like if you want to reset in other positions.
If you had a different initial condition, let's say if they were uniform, or let's say they were in a certain way, all that information will wash away, is it, at late times?
Yeah, for the resetting event, yeah, that event will wash away.
But you'll reset to the same initial condition, right? Let's say all the particles were distributed on a line from a Gaussian, let's say, or a uniform. you're saying these results are independent of initial conditions.
I think like qualitative feature will be same, but let's say you will see some effects in coefficients, not in the like temporal behavior and all.
Okay.
That I mean.
Thank you, Saikat.